Welcome back to our AP Chemistry Notes over titration. I want to wrap up with this video about a particular type of titration called a redox titration. So with the titration, we used an unknown acid to find out a known base. Well, I said that backwards. How about a known acid to find an unknown base, or a known base to find an unknown acid? With a name like redox titration, you can imagine we're actually going to find a known something being reduced to calculate an unknown something being oxidized, or a known something being oxidized to calculate a known something being reduced. So it really, in the most general of terms, works just like an acid-base reaction, only it's not an acid-base neutralization, it's a reduction-oxidation reaction where something's being oxidized, something's being reduced, and knowing something for one of the two allows you to calculate the other. It's not nearly as difficult as you think it is, and I don't know why year after year students make it out to be super hard. It works very, very similar to a acid-base titration. It just is a reduction-oxidation titration instead. So let's give an example. What volume of this amount of potassium permanganate is required to oxidize that amount of iron to sulfate? Here's the balanced chemical equation. And I know it's balanced because I checked the coefficients and I'm like, yeah, I see that it's balanced. Don't take it for granted on the AP test that an equation they give you is ever balanced until after you've double checked. Now, if they claim the balanced equation for blah, blah, blah is below, then yes, most definitely it's balanced if they say it is balanced. But if they don't say anything, just check it. It's 5 seconds and it's going to be well worth it. So here's our balanced chemical equation. I have incomplete information about potassium permanganate. I don't see any potassium permanganate. Well, okay, the part of potassium permanganate I probably care about is the permanganate part. Okay, sure, I can handle that because the potassium is going to be constantly soluble, so it's a spectator ion, so yeah, why bother with that? And I do have total complete known information for my iron 2 sulfate. Well, I don't have iron 2 sulfate. Oh, well, I do have iron, and that's probably the part of the iron 2 sulfate I care about because when the potassium and the sulfate get together, it's still going to be soluble. So I'm really looking at the permanganate turning into manganese ion and the iron 2 turning into iron 3. That might be the hardest part of these type of, I don't know what else is hard about this. Okay, so if this is difficult, that might be the most difficult part, is figuring out which parts to focus on. Do I care then about the hydrogen and the water? Not a bit. As far as I'm concerned, they don't exist. Okay, so what do I have complete information for? I have complete information for the iron ion. So let's start with that. So I'm going to start, and this is how I like to start. Check this out. I'm not starting with iron. Okay, check this out. I'm starting with my iron sulfate because that's what they give me in the problem. My volume times my molarity. So milliliters is going to cancel milliliters. And then I get moles of iron. For every 1 mole of iron sulfate, I get 1 mole of iron ions. And you're saying, duh, I already did that in my head. Well, yes, but trust me, the moment you try to skip that step is the moment the number is other than a 1-to-1 ratio, and then you're going to mess it up. So I strongly recommend show that step, please. Or at the very least up here, so show something like, now that's going to equal 1 iron 2 plus. So you at least have looked at that. Because if that was, something else, if that was an iron 3 ion, it's not a 1-to-1 ratio anymore. So be careful, please. Please, please, please. I know from my balanced equation that 5 moles of iron ion will reduce or oxidize. It doesn't really matter, okay? Now let's look at this. Here, manganese is being a +7. Here it's being a, oh, that should be a 2+ there. Like there's no such thing as a manganese with a 2 minus. Sorry. Here's a +2. So that's reduction. So therefore, 5 moles of iron oxidizing is going to be equivalent to 1 mole of permanganate reducing. Okay. Did I need to know which was which? And again, no, I did not. What I cared about was those numbers that came from the balanced chemical equation. That's all I cared about. And again, I'm ignoring the hydrogen and I'm ignoring the water. It doesn't freaking care. Okay, so get rid of them if they're bugging you. I don't know how to convince you these aren't hard. I'm still using information I've been given. None of this is anything I have to think about. Now here I do like doing this. I solve for 1 mole of permanganate ion, and 1 mole of permanganate ion would come from 1 mole of potassium permanganate. And again, I strongly recommend showing that step. Even though it's a 1-to-1 ratio, I would recommend showing it because the time that you don't, it's going to be a 1-to-2 ratio or a 3-to-2 ratio or 1-to-5. It's going to be something else. And then you're going to mess it up. So I like this step to show the ratio. And moles of permanganate cancel and I have moles of potassium permanganate. And using my inverse molarity, again, this is the inverse of the molarity I was given right here in the problem. Using my inverse molarity, I've solved for milliliters. Now the question did ask what volume, so I could have solved for liters just as easily and that would have been fine. The point is, of course, that you get either 40 milliliters of potassium permanganate or 0.04000 liters, one of the two. Okay, so it works exactly the same as an acid-base reaction. It is now a oxidation-reduction reaction. What you want to watch out for is when the ratios are not 1-to-1. Okay, that's where I would account for it in those steps. Could you do that in your head? Could you do it off in the margin? Oh, absolutely. But you need to do it at some point in time in the problem, or you're going to get it wrong. Okay. What is the molarity of sodium sulfite if 20 milliliters of sodium sulfite are titrated with 36.30 milliliters of 0.05130, yeah, I probably just started typing in random numbers, of potassium dichromate in sulfuric acid? Okay, now first off, in sulfuric acid doesn't make a bit of difference because we already did balancing in acids and bases, and I already have a balanced equation, so there we go. But that was there simply to tell me if I didn't have a balanced equation that, hey, I would have to do my balancing in acidic solution. So that didn't matter, so this part doesn't matter, and this part doesn't matter. So what's really going on? I have my dichromate turning into chromium. That's chromium. Oh, we're going to have to come back to that. Hold on to that thought. And I have my sulfite turning into sulfate. Okay, so now let's talk about that. Dichromate has a -2 charge in total. That I have a -14 from 7 oxygens, but leaving 2. That means my total negative side is a -12. So to cancel that, my positive side's a +12 divided by 2. Each chromium's worth 6. So chromium's going from a 6 to a 3. That would be reduction. And by default, then that must be oxidation. La-di freaking da, it doesn't matter to the question, honestly. So I don't know why these are harder than an acid-base question. So I'm going to start with that which I have complete information for. I have complete information for potassium dichromate, so I'm going to start with that. So here's my volume of potassium dichromate, and here's my molarity written as moles per 1,000 milliliters, and milliliters cancel. And the great thing about this video is if I talk too fast, you can pause and continue copying down. And here's my moles of potassium dichromate. And I want to do this. You want to do this step. It's a 1-to-1 ratio between potassium dichromate and dichromate. I get that, but what if it had been between potassium dichromate and potassium? Then it would be a 1-to-2 ratio, and you would have killed it starting here if you had not looked at your ratio. Now, from my balanced equation, it's a 1 mole of dichromate is 1 mole of sulfite, and so dichromate cancels, and 1 mole sulfite comes from 1 mole of sodium sulfate, and there's my moles. Oh, you're right. I did not find the molarity, I just found the moles. Well, that's okay. Now that I know the moles, I know that it's in 20 milliliters or 0.020000 liters. And so I just do the math, and there I go. There's my molarity of sodium sulfate, and I box that. So really no different than we were doing before with an acid-base titration. You just want to watch out for how many ions are from a compound. It's these steps where you check your ratio of ions to compound that's new. That's it. And notice I would expect you to be able to tell me which one's being oxidized, which one's being reduced, but I didn't need to know that to answer the question. I didn't even need to know how to balance it in acidic media because it gave me the balance equation to start with. So everything we've been doing leads up to this point. I hope you recognize that. We've been doing acid-base titration because they're a little simpler because they don't have these steps here. But that's the only new addition. So redox titrations are just as easy as acid-base titrations as long as you are consciously double-checking your ion to compound ratios. So check your ratio, and check your ratio. Okay. And you knew this day was coming. It's your turn. So pause the video, give it a try. If you don't find this to be easy, please figure out what's going wrong, and you won't know that. You won't know that you're doing something that's getting it wrong until you try. So pause the video, pause the video. Yes, I'm talking to you. Pause the video. You better have paused it. If you're back and you haven't paused it, or you're still here and you haven't paused it, you better pause it. Okay, so my complete information, notice I'm not even reading the question yet because I'm immediately recognizing I've got milliliters and molarity and milliliters. And so my completed information, I've got 40 milliliters of a 0.1442 mole per 1,000 milliliters. Ah, did I get you? Yeah, look at how powerful it is to do a railroad track. You're like, wait, that's milliliters and milliliters is there, and oh, sorry, and that doesn't match up. You're absolutely right. So if you had not tried it yourself and you're trying to copy down what I'm doing, see, I gotcha. And if you did it right, congratulations. And if you were yelling at the screen telling me I was doing it wrong, congratulations. And since I have milliliters on top, I want milliliters on bottom. So I'm going to put that 1,000 milliliters down there and my moles up here. Now the other thing that students often confuse is I have 2 milliliter amounts, so don't confuse the two. If you need to make some little T-chart to tell you what you know information for, that might be a benefit. Okay, so milliliters cancels milliliters. I've got moles of sodium thiosulfate, but I care, oh look, I do care about sodium thiosulfate, so there we go. So I have, it's a 1-to-1 ratio. So I'm not going to do anything there. Are you okay with that? I know I've said check your ratio, but I checked it's a 1-to-1 ratio, so I really don't need to show that. So I'm going to move on. How many moles of sodium thiosulfate will oxidize or reduce? I haven't checked which, I don't care which. Will oxidize or reduce the I2? Is that what I'm looking for? What is the molarity of the I2 solution? Yes, that's what I'm looking for. Okay, check it out, 2-to-1 ratio. Okay. Now, I know moles of I2, I'm looking for molarity, I want some moles per liter. Oh wait, I have moles. The only part I'm missing is the liters part. Do I know a liters part? Please tell me yes. 0.02636 liters. Where did I get that? Oh yeah, right there in the question. And now I get moles per liter, and so I'm going to get my molarity. Can I really string that into my railroad track and have a box on the top with nothing but a 1 in it? Absolutely. Okay, this is my railroad track. I bend it to my will. I don't let it tell me what to do. But when I need a guide to be sure that I'm putting the numbers in the right boxes? Oh yes, I most definitely let my railroad track guide me on the random off chance that I'm wrong. Of course, I, Mr. Bellman, would never be wrong, but the potential's there that you could be, and it would help guide you and keep you on the right path. Okay, so I'm going to take the 40 and I'm going to divide by 1,000. I'm going to multiply by the 0.1442. I probably just randomly typed in some numbers to get that, and I'm going to divide by 2, and I'm going to divide by 0.02636, and I get the molarity straight out of the calculator at 0.0, how many sig digs? I see 4444. Let me go for 4. So 0.1094 molarity of I2. There we go. So we're going to do a titration like this in lab, and it could be as simple as this. It does not have to be difficult at all. Now, what really helped this issue was I skipped in between there what I had shown earlier as a how many ions per compound step. Because I could have taken the sodium, so I really should, in the net on equation, take the sodiums off of this. But you know what? That's fine. It still serves the purposes. I'm letting my railroad track be my guide. I'm starting with that which I have complete information for, and I'm solving for that I have incomplete information for. And as long as I stay focused on that, I really have a very good shot of getting it right, and so do you. So that's all there is to redox titration. It is not more difficult than an acid-base titration. It might have some ratios in there you need to account for. But in and of itself, it is not more difficult than an acid-base titration, and it works. If something, as we said long ago, if something's reduced, something else has to be oxidized. And so knowing one, you can calculate the other. Another very powerful tool that we can use titration for. Okay, so you've done a ton of colorimetry. I know you love colorimetry by now. Now we're going to be doing a ton of titrations. You're going to love titrations. But they're all very useful tools in your chemistry toolbox to discover nature around you and unknowns and be able to calculate things that you never thought possible, which truly are possible to calculate. So good luck on your assignment over this. And of course, the point of doing the homework in class is that you get asked for help. So when you get to the point of do you need a ratio or not, please, let's discuss that. I'd rather discuss it with you during the homework time than after the test in May, because then it's too late. Good luck.